Okay, good morning everyone. So yesterday I uploaded the tutorial sheet number 1. So I'll show you. Yeah, so the tutorial sheet I have sent by email also, and I have uploaded it on MS Teams also. So if you go, there is a folder called tutorial, and in that you can find. And these lecture notes also I am uploading just after the lecture class. So you can see that also. So the first tutorial class will be held on this Monday at 1 o'clock. So the first tutorial sheet will be discussed. So you should try that and then come to the tutorial class. And the link for the tutorial class will be shared by the TA. And then you can join that link to attend the tutorial class. So, okay, so we were talking about norms on finite dimensional vector spaces. So what our aim is today to first prove that any two norms on a finite dimensional vector space are equivalent. So first we proved, so recall that on Rn or Cn, this one norm and infinity norm are equivalent. This is because you can see that for any x, the infinity norm of x is less than equal to the one norm, and one norm is less than equal to n times infinity norm. Also, if you consider the two norm and infinity norm, then the two norm, this is again bigger than equal to the infinity norm, because the two norm is summation of mod xi square. So that is clearly bigger than equal to the maximum of mod xi squared, and then you take the square root to get the two norm. So you get norm x infinity is less than equal to norm x2, and this is less than equal to square root n times norm infinity, right? Because again summation of xi square that is less than equal to n times the maximum of this xi square and then mod xi square, and then you take the square root, so you will get this is less than equal to. So this norm 2 and norm infinity are also equivalent. So in fact, all these are equivalent norms. So hence the topologies induced by norm 1, norm infinity, and norm 2 are the same. So what we will prove is that in fact any two norms are equivalent, so they will induce the same topology. So this we get. Now what do we get from this? So suppose I take the closed unit ball in one of these, so say norm 1. So let me write this lemma. The closed unit ball in L1n is compact. So that means that on Rn or Cn, if you take uh, the L1 norm and then look at the norm, so that is this x such that norm x1 is less than equal to 1. This is compact. So because we know that these topologies are same, so here when we say compact, in the norm linear space, we are taking this L1n. So by the above remark, we know that norm 1 is equivalent to the Euclidean norm, norm 2. And what do we know in the Euclidean norm? A subset is compact if and only if it is closed and bounded. Right? So if we know that this is closed and bounded set, then in the Euclidean space, then we know that it has to be compact. So, so the proof is simply that let me just write so that let me write this set as B. B is closed and bounded in this L2n. Right? Of course, it's a closed ball. that is closed in that norm. So again, closed is not a problem because the topologies are same. So for any non-linear space, if we look at the closed ball, that is a closed set that you can prove in general. So it will be closed in L1n, and that topology is same as the topology of L2n, so it is closed there also. Bounded, the again, because these norms are equivalent, so if it is bounded in one norm, then it will be bounded in two norm also. So both these things follow from the fact that these two norms are equivalent. Norm 1 and norm 2 are equivalent. So therefore, this will imply that B is compact in the space L2, but since the two topologies are the same, this B is compact in L1. So this is done. Now let's prove this theorem. Any two norms on a finite dimensional vector space are equivalent. So let V be a vector space of dimension say n. So we will show that V is isomorphic to L1n. And as a vector space, you know that if you have a vector space of dimension n, then it is isomorphic to Fn. So if you have a real or complex vector space of dimension n, then it will be isomorphic as a vector space to Rn or Cn. But here when we say isomorphic, then we also require that the topologies are also the same, which is the same thing as saying that the two norms are equivalent. So to see this, uh, we have to define an isomorphism from V to L1. So let E1, E2, En be the standard basis of L1n, so Rn or Cn, whatever. You take the standard basis and let V1, V2, Vn be a basis of V. So now we will define an isomorphism. So define T from V to L1n by, or let me define the other way. So if I define from L1n to V by T of, if I take any summation alpha I ei, I equal to 1 to n, then I'll map this to summation alpha I vi, which means that you map these basis vector to these basis vectors. So T of E1 is V1, T of E2 is V2, T of En is Vn, and then you extend it linearly. So we get a linear transformation, and we have to show that this is, I mean, this is of course 1, 1 on 2, and it's a linear transformation. So clearly T is 1, 1 on 2 and linear. Now we will show that this T is continuous and T inverse is also continuous. So T and T inverse both are bounded linear operators. So, so why is T continuous? So this just like we proved that L1n to, if we had any norm on Rn, then we showed that that is bounded. So similarly we can do for this. So if you look at T of, if x is equal to summation alpha I ei belongs to L1n, then T of x is summation alpha I vi. So if we look at norm of T of x, that is norm of this, and this by triangle inequality is less than equal to summation I equal to 1 to n mod alpha I times norm of vi, which is less than equal to maximum of norm vi, I varying from 1 to n. This is a constant times summation of mod alpha I, but summation mod alpha I is nothing but the norm of this vector x in L1n. So this is equal to norm x1. So norm of Tx is less than equal to some constant times norm of x. So this implies T is bounded. Next we will show that T inverse is also continuous. This is claim 1. into T inverse is also continuous. So we'll prove this by contradiction. So suppose T inverse is not continuous, then we can find a sequence. There exists a sequence it's called yn in V such that so that there exists a sequence and an epsilon positive such that this norm of yn goes to 0, but T inverse of yn. So T inverse maps from this vector space, the nonlinear space V to L1. Okay, so here I'm taking this vector space with some norm. So I should write this V is so let this V with norm be a norm linear space right. So we will show that this non-linear space is isomorphic to L1n. So T inverse is a map from V to L1. So if T inverse is not continuous, then that implies that it is not continuous at 0. So I'll get a sequence converging to 0, but T inverse of that sequence yn does not go to 0. So that means that I can find an epsilon such that the L1 norm of T inverse yn, this is bigger than equal to epsilon. Right, so this just follows from the fact that this T inverse is not a bounded linear operator. So we get this. Now let Zn equal to yn by the L1 norm of T inverse yn. So we know that this norm T inverse yn, this is strictly positive. So I divide this by this. So then Zn will converge to 0. Why is this? This is because if we look at norm of Zn, this is equal to norm of yn divided by the one norm of T inverse yn. But norm of T inverse yn is bigger than equal to epsilon. So this will be less than equal to 1 by epsilon times norm yn. And we have this sequence yn going to 0. So this goes to 0. So Zn will converge to 0. And what about T inverse Zn? T inverse Zn is nothing but T inverse Yn by the one norm of T inverse Yn. So if we look at the one norm of T inverse Zn, this is equal to 1 for all n. Right, so T inverse Zn has norm 1 and Zn converges to 0. So can this happen? So this T inverse Zn if we look at this sequence is a sequence in the compact set. This B that we defined, X as that. So I have a sequence in a compact set. So if there is any sequence in a compact set, then it must have a convergent subsequence in a metric space, right? So this will imply T inverse Zn has a convergent subsequence, say T inverse Znk converging to let's say some x. So T inverse Znk converges to x. So if T inverse Znk converges to x, and we know that norm of T inverse of Znk is equal to 1, since norm of T inverse Znk, this is equal to 1 for all k, norm of x1, this is also equal to 1. So x is a unit vector and T inverse Znk converges to x. We already know that T is continuous. As T is continuous, T inverse Znk converging to x implies Znk, which is T of T inverse Znk. This will converge to T of x. So Znk converges to T of x. But what we know is that Zn converges to 0. So this implies T of x is equal to 0, since Zn converges to 0 as in this. So Tx is equal to 0, but Tx is equal to 0. This will imply x is equal to 0. Right? Because T is given to be a bijection, since T is 1, 1. But we know that norm x1 is equal to 1. So this contradicts. Norm x1 is equal to 1. So this contradiction is because we assume that this T inverse is not continuous. So hence our assumption that T inverse is not continuous must be 1. So therefore, this T inverse is continuous. So what we have proved is that this we have shown that this V with the norm is isomorphic to L1N. So if we have any two norms, then both are isomorphic to. So if norm 1 and norm 2 are any two norms, on V, then this V with norm 1 and V with norm 2 both are isomorphic to L1N, which implies these two norm linear spaces are isomorphic, and hence norm 1 and norm 2 are equivalent. Is this clear? So the main idea is simply showing that if we have any finite dimensional non-linear space, then you show that that is isomorphic to L1N. Once you have shown that, then you get that any two norms are equivalent. So
So for infinite dimensional case, it will not be so.
yeah, for infinite dimensional, it is not true. So I'll give one example. So first, let's see an important corollary to this result, this theorem. So as a corollary, we'll get that any finite dimensional non-linear space is complete, which means that any finite dimensional non-linear space is a Banach space. And in particular, any finite dimensional subspace of a non-linear space is closed. Right, so it is clear that any finite dimensional non-linear space is complete. This is because we showed that if V with norm is a finite dimensional non-linear space, then that is isomorphic to L1N. And L1N is complete, therefore this will be complete. So if you take any Cauchy sequence in a finite dimensional non-linear space, then because this is equivalent to the L1 norm, therefore you get a Cauchy sequence in Rn with respect to L1 norm, and that we know that it must converge, and therefore this will converge. And the other one follows because if we have any finite dimensional subspace of a nonlinear space, then that is a finite dimensional nonlinear space, so it must be complete, and any complete uh, subset of a metric space, it must be closed. So we get this. So next, let's show that on infinite dimensional nonlinear space, we can have two norms which are not equivalent. Remark. On an infinite dimensional nonlinear space, we may have two norms which are not equivalent. So let's look at example. So consider C01. C01 means all continuous uh, scalar valued functions on the closed interval 0, 1. So here we have seen two norms. We have seen a norm which is we denoted by infinity norm. So with this is defined as supremum of mod ft t belonging to 0, 1. In this case, the supremum is actually the maximum. So this is one norm. Also, we will define another norm. Define another norm on C01. As norm f1, this is equal to integral of mod ft dt from 0 to 1. So this is the capital L1 norm restricted to this C01. We have defined the capital LP spaces where we take integral of mod f to the p dt and 1 by p. So for p equal to 1, we get the L1 norm. So this is again a norm on C01. So now we have two different norms. We will show that these two norms are not equivalent. So to show that these two norms are not equivalent, let's look at a sequence. Consider the sequence Fn in C01 defined by Fn of x. This is equal to 1 minus nx if x is between 0 and 1 by n, and it is 0 if x is bigger than 1 by n. 1. So this Fnx is simply this function where up to 1 by n you have at 0 it is 1, and then you join by this straight line from 0 to 1 by n, and then it is 0 up to 1. So this is the function Fnx. Then what is norm? The sup norm of this Fn. See, Fn of 0 is always equal to 1, and this Fn mod Fnx is always less than equal to 1. So this is equal to 1 for all n. Right? The infinity norm of Fn is equal to 1. What about the 1 norm? So how do we define the 1 norm? This is the integral of mod Fn t dt. So the integral will be the area under this graph of this function. What is the area of this? So that is equal to area of this triangle. Height is 1 and the base is 1 by n. So this is equal to 1 by 2n. So does this imply that these two norms are not equivalent? Therefore, norm 1 is not equivalent to norm infinity. Because otherwise, this norm of Fn infinity, this will be less than equal to some constant times norm of Fn1, right? If these are equivalent, then the infinity norm is less than equal to some constant times the 1 norm, but the infinity norm is equal to 1 for each of these n, Fn, and the 1 norm is C by 2n. So this shows that 1 is less than equal to C by 2n. This is a contradiction, right? So this goes to 0, then goes to infinity. So this cannot happen. So on infinite dimensional nonlinear space, you can have norms which are not equivalent. Okay, any questions so far? All right, so
Can we generalize it to any other field, like without Rn or Cn?
sorry.
If we take any arbitrary field, then can we generalize this norms?
So non-linear space is always defined for field of real or complex, right? So what do you mean arbitrary field?
For arbitrary field, we not define this.
Okay, can you define norm on an arbitrary field? Let's say space over arbitrary field. This we discussed in the first class itself, right? How do you define norm? One property is that norm of lambda x is equal to, what is norm of lambda x?
Mod lambda norm x.
Mod lambda times norm x. What do you mean by mod lambda for arbitrary field?
Okay.
We don't have any such thing, right? So non-linear space, when we say, it is always over field of real numbers or field of complex numbers. So we call real non-linear space or complex non-linear space. And everything that we are doing so far is true for the real as well as complex non-linear space. So I'm not like writing what the field is. It is true for the field of real numbers as well as field of complex numbers. Is it okay? All right. So
Yeah.
the next important result that we are aiming for is that we will show that uh, okay, so what we have seen is that because any two norms on a finite dimensional non-linear space, they are equivalent. So therefore, if we look at any finite dimensional non-linear space and you look at the closed unit ball, then it is always compact, right? So let me write this. So we have that the closed unit ball on a finite non-linear space is compact. This is because we proved that V is isomorphic to L1N. So you're using that. You can see that because the closed unit ball on L1N is compact. You can so this thing is true. So the important thing is that the converse is also true. So if the closed unit ball is compact, then the space has to be finite dimensional. So we will see that this is actually a if and only if statement. So, so so compactness of the closed unit ball, that actually characterizes the finite dimensional, not finite. So this is on a finite dimensional. We will see that if the closed unit ball is compact, then the space must be finite dimensional. So to prove this, we need one lemma, which is called Ree's lemma. So let me state the Ree's lemma. So let V be a non-linear space and let W be a closed proper subspace of V. So V is any non-linear space, and W we are taking as closed and proper subspace of V. Then given any epsilon positive, we can find a vector. There exists U in V. So this will depend on epsilon. So given epsilon, you get a vector U. This is depending on epsilon, such that U is a unit vector. So norm U is equal to 1, and distance between U to W is greater than equal to 1 minus epsilon. Right. So what this is saying is that if you take any proper and closed subspace, then you can find a vector, unit vector in V such that its distance is bigger than equal to 1 minus epsilon for any epsilon positive. So you see that this says that actually you can get a sequence such that the distance between U to W actually goes to 0, right? Because this you can make bigger than equal to any number smaller than 1. So, and what is the distance between a vector to a subset? That is just the infimum of, I'll write distance between U to W. This is infimum of norm U minus W for W belonging to W. Right? So this is distance of a point from a subset in a metric space is defined as infimum of distance of U to any point in that subset. So this is what we have. So let me just do this proof and then we'll stop. So first of all, since W is a proper subspace, we can find a vector which is not in W. So there exists V belonging to V minus W. We have a vector V which is not in W. So then if we write delta equal to distance of V to W, what can you say about delta? Can it be 0?
No,
No, why?
because V is not a point of W.
Okay.
Sorry, say again.
W is close to W bar is W. We should be in W notes.
Right, because W is closed, right? So because W is closed, so this has to be bigger than 0. This is because W is closed. So we need that the subspace is closed also. So because if the distance of V to W is equal to 0, that will imply that V belongs to W closure. But W closure is same as W, but that will say V belongs to W. But we have chosen V not in W. So delta is a positive real number. So now, of course, we can assume that this epsilon is less than 1, because if epsilon is greater than equal to 1, then we have nothing to prove, right? So given epsilon greater than 0 and less than 1, let me just write that if epsilon is bigger than equal to 1, then nothing to prove. Right, because duv bigger than equal to 1 minus epsilon, that will say that I mean, you can always find there's some vector and distance of u to w is always bigger than equal to 0. So that is close to. So if we have any epsilon between 0 and 1, we can choose u, let's call w in capital W, such that norm of u minus w, this is less than equal to delta by 1 minus epsilon. Right? Delta is what the infimum of norm v minus w, where w is in capital W. So if we look at delta by 1 minus epsilon, then this is strictly bigger than delta. So we can now always find vector w such that norm of u minus w is bigger than equal to, is less than equal to delta by 1 minus epsilon, and this is clearly bigger than equal to delta, because delta is the infimum of all these things. So norm of u minus w is between delta and delta by 1 minus epsilon. So now we will define the vector u, which will do. So let's put u equal to v minus w okay, this is not u, this was v. So this is v minus w by norm of v minus w. So if we write u equal to v minus w by norm v minus w, then first of all, norm of u is equal to 1, and we have to see that d of u to w, this will be bigger than equal to 1 minus epsilon. This is what we are claiming. So claim is d of u to w is bigger than equal to 1 minus epsilon. So for this, we have to take any vector in w and show that the distance of u to w is bigger than equal to 1 minus epsilon. So let z be any vector in w, then u minus z norm we have to show that this is bigger than equal to 1 minus epsilon. So what is u? U we have written as v minus w by norm v minus w. So this is v minus w by norm of v minus w. Hello, am I audible?
Yes.
Okay.
Yes, sir.
So this is equal to v minus w plus norm v minus w times z divided by norm of v minus w. Now note that w is a vector in capital W and z also we have taken in w. So this whole thing, this belongs to w. So we have norm of v minus a vector in w divided by norm of v minus w. So the numerator is bigger than equal to delta, right? Because delta was the distance of v to w. So the numerator is v minus a vector in w. So that is bigger than equal to delta. And the denominator norm v minus w we saw is less than equal to delta by 1 minus epsilon. So 1 by norm v minus w will be bigger than equal to 1 minus epsilon by delta. This is delta by 1 minus epsilon, which is equal to 1 minus epsilon. So we have shown that the norm of u minus z is bigger than equal to 1 minus epsilon. So, so therefore, d of u to w, this is infimum of norm u minus z. Z belongs to w. This is also bigger than equal to 1 minus epsilon. So hence we are done. Okay, so I'll stop here. So next class, I'll prove using this Rees lemma that the closed unit ball compact will imply that the space is finite dimensional.